Hello, class. Welcome to the next section, chapter 9.2. Today we are going to talk about trigonometric integrals. So, uh, what we're going to do is we're going to look at how we can use trig identities, how the values of the powers present of different trig functions um, will help us to integrate products of trig functions. Okay, so very similar to the last section where we're looking at products of functions. One was f, one was g. We're doing integration by parts. Here, we will be using identities, and actually, we're just going to really mostly be using trig identities in order to integrate different uh, powers of products of trig functions. Okay, so we'll kind of break these down one by one, case by case. Then we'll do an example as necessary. So first, let's look at our approach when dealing with functions of sines and cosines. So when we have functions of sines and cosines at different powers being multiplied, so generally in the form of sine to some degree times cosine at some other degree. Okay. And now you might say, um, what about other functions like sines and tans? If we have mixtures that are not sines and cosines, or the next mixture that we'll talk about, generally you can you just break down tangent into sines and cosines and mix them together, right? So whenever we have sines and cosines mixing together, they have a lot of relationships between them, so there's a lot of identities that we're allowed to use. So let's look at our first case. Um, the main idea is basically that we're going to get everything down to either a single cosine or a single sine, okay, for the most part. So let's say that we have an odd power of cosine, right? So let's say this is like cosine cubed, cosine to the fifth, cosine to the seventh, cosine to the ninth, some odd power of cosine, right? If you did not know, odd powers can be, or odd numbers, period, can be uh, shown as 2k plus 1, where k is some integer. Okay, so any odd number has this form, right? So again, k is some integer, doesn't matter which one. And so that's how we get all odd numbers. So basically, what it's saying is that an odd number is some even number, right? Two times anything is even. So some, or any whole number, I should say. So any even number plus one is odd, right? So anything that looks like this, odd power of cosine. Again, we're looking at n specifically here for cosine. Uh, our goal is to save one cosine, and then we're going to use the common trig identity of cosine squared plus sine squared equals 1, but obviously solve for cosine squared um, for the rest of the cosines that we have. So remember, we have an odd power here. So we save 1. That means that we have an even number left. So it should be some multiple of cosine squared. So um, whenever we have an odd power of cosine, we save one cosine, and then we use this identity for the rest of the even ones that are left. Okay. So what it will look like in general, like this is kind of just to get you started. We have m powers of sine, n powers of cosine, where n is odd. So we can replace n with 2k plus 1. Okay. I'm going to pull one cosine out. The rest of these are squared, so I'm going to have k of them. If you combine this together, you'll notice that I have 2k plus 1 more, right? 2k plus 1, there's odd numbers here. So all of these cosine squares, the k of them that I have, I can now rewrite with this substitution, 1 minus sine squared, okay? And there's again k of them, because that's equal to cosine squared. And then from here, I would just use some sort of a u substitution. Generally, I'll let sine, just a standard sine, no powers, be my u. And then the derivative of sine is cosine. And so again, this cosine x dx then would turn into the du. And then everything here would just be sine, right? This would be u to the m times 1 minus u squared to the k. That's just a polynomial at that point. Very, very easy to simplify and to integrate after that. So that is an odd power of cosine. an odd power of sine, we do the exact same thing. Okay. Okay. So we take m as 2k plus 1, an odd number. We're going to save one sine instead of saving one cosine and save one of those, one of the sines. And we use that trig identity of sine squared x is 1 minus cosine squared. And that's going to make all of the rest of our functions nothing but cosines. Okay, so we save one sine, turn everything else into a cosine with the squared property. Okay, with the circle identity. So sine to the n of x, cosine to the n of x. Replace m with 2k plus 1, some odd number. Um, n here could be even or odd, it doesn't matter. Okay, we save one sine. Then we have sine squared, and there's k of those, right? Multiply powers here, so there's 2k plus 1 more. So we pulled out 1 to save, and then we kind of separate this into a bunch of sine squares. We plug in our identity. Okay, so that sine squared turns into 1 minus cosine squared times a cosine to the nth power. And this is my sine of x. So then I let u equal sine of x. Okay, or I'm sorry, cosine of x. Then when I take the derivative, cosine changes signs. So it's a negative sign. And so then I have a negative du. And all of these are just u to whatever power, right? Turns into a polynomial in u. Now, if both of them are odd, if sine is an odd power and cosine is an odd power, you have your choice. Pick whichever one you want. You could stick with sines or stick with cosines. It doesn't matter. It'll work either way. Okay. Maybe one is easier than the other. Maybe there's less cosines than sines. Maybe there's less sines than cosines, and maybe it's easier to deal with. Okay. Now let's go to the complete opposite of that, which is that none of them are odd, right? So what do I do when they're both even? Well, it's not easier, but there's an option. There's more identities for when you have two even powers of sine and cosine. So there's the double angle identities, such as sine squared is 1/2 1 minus cosine of 2 of x. There's the cosine version, which is identical, but it's 1 plus cosine of 2 of x. Okay, so you can use either one of these. So you have nothing but cosines and nothing but sines, or you can do the sine cosine identity, which equals 1/2 sine of 2 of x. So any of these double angle identities are perfectly okay for um, for solving when they're both even. Okay? Note that if you plug in a 2x here, you're getting a 2 times 2x here. So that turns into 4x, or here, right? If this is sine of 2x, cosine of 2x, this turns into sine of 2 times 2x, right? If this is a 3x, it turns into 1 minus cosine 6x here, right? So make sure you remember how to plug in things into a function, okay? It's a common thing that happens to calculus students because possibly they're not used to doing that after algebra, right? So make sure if you are changing these identities, you're changing it equivalently, right? Okay, so same thing here. All right, so let's do an example. Um, integrate sine to the fourth power times cosine to the cubed power. So obviously cosine is the one that is odd. And so since cosine is odd, we save 1 and we keep a multiple of cosine squares, which is really just 1. So we'll split it across and we'll change the cosine cubed into cosine squared times cosine. I'm going to plug in my identity here for cosine squared. So this is going to turn into 1 minus sine squared. Okay. So now I got a bunch of sines and this cosine. So I'm going to let u equal sine so that this turns into basically a polynomial in u. And the derivative of sine is just cosine. So that'll be very, very helpful. So this will turn into du for me. Plug everything back in. I'm going to get u to the fourth times 1 minus u squared, and then my du. This is just a polynomial. This is u fourth minus u to the sixth. I'm not going to write it out because you guys should be able to figure that out. Don't do some weird substitution thing here. Just multiply it through. right? So the integral of u to the fourth is 1/5 to the u, uh, 1/5 uh, u to the fifth. Here, this is u to the sixth, so it turns into 1/7, u to the 7 plus c. Again, don't forget to go back into x's. So I'm going to replace all of these u's with sine of x. And that is how we integral products of trigs. Okay. Let's do another example where we change it up a little bit. Here, cosine was the one that was odd. Here, none of them are odd. I have two evens, right? So for this one, I would use one of these double angle identities, okay? Whichever one seems the most appropriate at the time. I can go into all cosines, or if I have a bunch of sines, or I can do the cosines, doesn't really matter, or I can do both. Here we go. So sine squared, cosine fourth, so we'll use both. Sine squared and cosine because then I have everything in terms of cosine of 2x. So I wouldn't want to do just sine or just the cosine squared because then I would have some mixed match cosines floating around. So I'm going to substitute both of those. So this will be the 1 minus cosine of 2x times 1/2, and this will be 1/2 times 1 minus or 1 plus cosine of 2x, and then I will be squaring that here, right? So here, so sine squared is this term, cosine to the fourth has the same thing, but again, it's a plus in the middle, and I'm squaring it, right? Because I would be doing it twice, right? If you need to multiply, expand this out for yourself to check and verify that it's equivalent, then that's fine. Go ahead and do that on the side. Just pause the video, okay? From here, let's go ahead and pull out these constant terms. I have a 1/2, and then this is a 1/4 because it's squared. So 1/2 plus 1/4 is 1/8. Then I have 1 minus cosine of 2x, and then two of these. I don't have to actually expand this right now. You'll see we can actually do something nicer than that. Um, but yeah, I have 1 plus cosine of 2x, 1 plus cosine of 2x, 1 minus cosine of 2x. So I just wrote this twice. I can expand the whole thing if I want to, which I'll probably end up doing. But first, let's go ahead and work with these because this is a difference of squares, if you notice this, right? Same term, 1 plus, 1 minus. So we can rewrite this as 1 minus cosine squared of 2x times this 1 plus cosine 2x. Okay. That's the rule of difference of squares. Um, and so from here, we can go ahead and multiply this through if we wish, right? So we got the 1, we have the cosine of 2x, the negative cosine of 2x, and the negative cosine cubed of 2x, right? So we're not going to try to factor this because we just unfactored it. So don't try to do some weird stuff and factor this because it was already factored. We just unfactored it, right? We just expanded it to term, so don't factor it. You just go in a circle. We're going to distribute this integral sign across, okay, into 4 different functions. And each of those 4 functions has a different way that we'll approach the integration, right? This one we can do a use substitution with a 2x. It's pretty straightforward. We've seen how to do this quite often. Here we have a cosine squared of 2x, so we're going to have to do a little bit of work here. And here, cubed x, we're going to have to do something different there as well. Okay, so first and foremost, let's spread this constant term across and this integral across. So you can see I just have 4 separate integrals here that I'll work on individually. This one is very straightforward. It just turns into 1/8 times x. Here, it'll be a 1/2. See, change the sign, sign stays the same. So this should be just a regular sine of 2x when I integrate here. And then these ones I'm going to have to do a little bit of work on. Okay. So here, this one turns into just 1/8x. Okay. This one I haven't done anything to yet. I'm just going to leave the same. I'm going to work on it later. And then we're going to start focusing on these things. So I have this square term. I'm going to use my um, double angle identity, right? Same one I was using before up here. I'm just going to use it again. Um, but it's a 2x on the inside, so that bumps it up to 4x. Okay. Here I have a cube power, so maybe I break this thing down, right? Same thing we are doing before. I have 1 cosine squared, and I pull out 1 cosine. So cosine squared, I know is 1 minus sine squared. And again, the inside is 2x, right? So I'm approaching each of these a little bit differently, okay? I'm going to let u be 2x. This is for the second integral here. Well, when I differentiate that, I'm just going to get du equals 2 dx, right? I'm going to have v equals 4x here. So when I differentiate that, I'll have dv is 4 dx. And for this one, I'm using the sign, right? Because when I differentiate this, the sign stays the same. I will have a cosine of 2x dx, which will be my dw, okay? So again, differentiating u, differentiating v, and differentiating w, okay? Now I can go ahead and make my substitutions into the last 3 integrals here that I have left. Of course, there is no 2 on the outside here, so it'll be a lot easier for me to refer to dx as 1/2 du. And so then I can just multiply this by 1/2 when I substitute this in. Same thing here. Let's solve for the dx. So this will be 1/4 dv dx. And same thing here. I don't have a full 2 on the outside. I do have a 1/8, but just to make it simpler, divide both sides by 2. Um, and now we can substitute, right? So this is 1/8 over 1 over 8 times x. This will be 1 over 8. Um, this u term is coming here, so times 1/2, and I will have a cosine of du. So this will be 1 over 16 cosine of u, which is easy to integrate. Here I have 1/8, 1/2, so that's 1/16. And for this one, I'm putting in a 1/4, so 16 times 4, so that's 64, I'm sorry. So I have minus 1 over 64, then just 1 plus cosine of v in this case, dv. Here I'll have 1/8. I am using 1/2, so then that'll be 1/16. So minus 1/16 integral of 1 minus u squared. And then this is just going to be my du, or in this case w, I'm sorry. So 1 minus w squared. So again, now it's much easier to integrate these. Cosine, we know, turns into sine. Signs stay the same, so this will just be turned into sines when I integrate. So this stays as a 1 over 8x. This turns into 1/16 times cosine of u, I'm sorry, sine of u. This is negative 1 over 64 times v plus sine of v. Okay. This is 1 over 16, so minus 1/16 w in this case, uh, plus 1/16. This will be a 1/3, right? So 3 times 16 is 48. If I when I decide to distribute this out, right, I could have done it right away if I wanted to, plus C. And so now let's just kind of simplify everything. So we can plug everything back in right now, or we can kind of work with what we have. Let's see what I chose to do. So I just plug everything back in. Okay, so U I replace with the 2x. I replace V with the 4x. So then this turns into the sine of 4x. I replace W with what it is as well. And so on this next term, let's start to combine my like terms. I have 1/8x. This negative 1/16 comes from this. This is the only other x term. So 4 over 16 is 1 over 16. Then I have plus 1 over 16 sine of 2x. Over here, I have another sine of 2x, which is the same thing, but negative. The next sign that I have is 4x, so I'm going to have minus 1/64 sine of 4x. And then the last thing is this cube. So again, this 1/16, this 1/3, they're both negative, so that turns positive. Okay. So for here, I can combine my like terms. I have two x terms. These are my sine of 2x terms. There's only one sine of 4x. There's only one sine cubed. So these last two can't combine, but the first two and the middle two can combine. So 1/8 minus 1/16, that's going to leave me with 1/16. And then these two will cancel. So I should have 1 over 16th x. And then these last, let's say 3 terms with the constant of integration. Okay. And from here, I can't really simplify anything. I can pull out and factor a constant if I need to, but that's unnecessary. So then that would be my answer. So 1 over 16x minus 1 over 64 sine of 4x plus 1 over 48 sine cubed of 2x plus my constant of integration, since this is an unbounded integral. All right, so let's do another example. Let's do the exact same problem, but instead of using the double angle identities for sine squared and cosine squared, let's use the third option of using pulling out a sine of x times cosine of x. Okay, so again, we come back all the way. So we use these two substitutions so that we can have some cosine of 2x's. The third option is to try to use this double angle identity, right? Sometimes this one might be easier than the others. Sometimes this one will be easier than this one. Just kind of have to go for it, right? So let's do these substitutions. We got our answer. So uh, I am going to try to save as sine squared cosine squared, and I'm going to pull out one sine squared to do that. So again, let's look at this identity. I need 1, right? So it's okay to pull out 2. They're being multiplied. I would just be squaring it in this case, right? So I'm going to separate out a cosine squared. So I have same powers of sines and cosines multiplied. I can just pull that power out, in this case, squaring it. Okay. Then I have that cosine squared that I pulled out. Substitute this identity that I have, right? The 1/2 sine of 2x. For cosine squared, I'll use its double angle identity, 1/2 times 1 plus cosine of 2x. Now I can multiply this through, block this 1/2. This will be 1/4. So 1/4 and the 1/2 is 1/8. Okay. I have a sine squared of 2x and 1 plus cosine of 2x. So from here, let's see, I just multiplied it through. Okay, so I could use that identity here, I guess, if I wanted to. But if I use the double angle identity here, it would bump it up to a 4x on the inside. All right, 1/2 times 1 minus cosine of 4x, since there's a 2x on the inside. So that wouldn't help because then I have cosines with 2x's on the inside. Things don't match up as nice, right? So um, as far as looking for other identities to do. So I'm going to go ahead and multiply this through. So sine squared of 2x plus sine squared of 2x times cosine of 2x. If I wanted to use another identity again here, I could, right? I could pull out one sine of 2x and do it again, but I don't think that will help me too much. So let's go ahead and use a second integral, right? We'll distribute this integral across. So sine squared of 2x here, probably have to use that half angle identity. In this case, here I have an odd power of cosine and an even power of sine, so I can just do what we're doing before, right? I just substitute in for this sine squared problem here. Here, let's go ahead and pull out this 1/2. This will turn into 1/16 here, and then I can just use the u substitution as normal for this one, right? Use 4x. Here, I'm going to have v is 2x. So again, doing like we would for an odd power of cosine. Okay, find the derivatives of these things. Isolate them because if you come back here, I don't have 2 of these. I do have a fraction, but we'll just go ahead and isolate this term. So divide this by 2, divide this by 4, right? Now it's a lot easier to just kind of plug and go. So this turns into 1 over 64, 1 minus cosine of u. And this turns into 1 over 16, integral of b squared of dv. Much easier, right? This turns into 1/3 b cubed. This turns into a u. This turns into minus sine of u. So things become very, very, very much cleaner now. Now we gotta resubstitute, right? U has to come back in, so this will be a 4x, sine of 4x. and v has to come back in. So this will be sine cubed of 2x, right? Let's go ahead and distribute this 1 over 64. So this turns into 4 over 64 is 1 over 16, and I can distribute this here, and I have the exact same answer that I had before. So I think that that's a tad bit less work compared to what we had before. It's a little, it's not a whole lot more. One might seem more straightforward than the other, so whatever is comfortable to you is really what you want to work on. Okay, so we have the same answer here as before. Okay, so as we saw before, those are all of our options for sine and cosine. Let's go over tangent and secant. We don't go into like cosecant and all those kinds of things. They're really just variations of what we have already, right? So we will talk about tangent and secant, and then that's pretty much it after that, okay? So again, we'll have kind of like three rules to kind of go for. Um, Powers of tangent, powers of secant. Again, if these were mixed up, let's say it was tangent and then this was like sine, I could just kind of manipulate my tangent here and then try to use some identities, right? But cosine and sine go very well together. They end up getting paired, and then tangent and secant do as well. And then we have to be crafty in our substitutions, which is what we're going over now, right? So let's say I have even powers of secant. So the n here is 2k. I'm going to save one of those squares, and I'm going to use the substitution for tangent and secant to turn everything into tangents, right? So secant squared is 1 plus tangent squared. So turn everything into uh, tangent, okay? So in general, it looks something like this. Tangent to the n power. Secant, in this case, has an even power. I'm going to pull out one of those evens, right? And then I'm going to be left with k minus 1 even powers, right? If you multiply this through, you'll see that it comes out to 2k, right? Multiplying this through is 2k minus 2, and then I have this plus 2 here, which brings me back to 2k, right? So I should have k minus 1 number of secant squares. Uh, I will turn those into 1 plus tan squares, right? And then everything is in terms of tangent now, and then this will be my du. So I'm going to say u is tangent. This turns into um times 1 plus u squared to the k minus 1 power. This will turn into du, right? So you differentiate tangent, you get secant squared, right? So now let's say that instead of secant having an odd power, tangent has an odd power. Sorry. Instead of secant having an even power, tangent has an odd power. So tangent is some odd value. We're going to save one secant times tangent, and then we will use the identity for that, which is tangent squared equals secant squared minus 1, as we saw before, for the rest of the tangents that are present. So that should have k number of tangents left, right? So replace m with 2k plus 1. Okay. I'm going to pull out one secant and one tangent, so this will turn into n minus 1. This will turn into 2k. Okay. So 2k tangents, that means there's k tan squares. There's one less secant. Secant and tangent get to kind of get held on to. Um, let's see, if I use the substitution, secant squared minus 1, everything's in secant. I'm leaving this one, right? So my u then here would be secant squared. When you take the derivative of secant, you get secant times tangent, right? So u is secant. The derivative of secant is secant times tangent, and everything will work out. So the only other one that we have to talk about is cotangent and cosecant, right? So we already have a secant term and a cosecant term. So this is kind of the only trig thing that we have left going on is cotangents, cosecants. And the same rules are going to apply for the tangents, right? If I have odd powers of cotangent, which is kind of pretty much just like a tangent, I'm going to apply rule number 2, right? Odd powers of tangent, odd powers of cotangent. I do the same sort of thing, right? I'm going to save one of these, the equivalent um, identity that we have for cotangent for the secant tangents. Okay. So I'm going to save a cosecant cotangent, and I'm going to use cotangent squared is cosecant squared minus 1. And I'm going to let my u be cosecant, and the derivative of that is negative cosecant cotangent. So again, look at the relationship here. It's pretty much the same thing. I save, instead of a secant tan, the reciprocal of that, 1 over secant, 1 over tangent, right? So cosecant cotangent. Instead of tan squared, it's cotangent squared. The identity is the same, it's just the reciprocals, right? Instead of u is secant, because everything is now in terms of secant, I use u as cosecant, the reciprocal of that, right? And everything works the same. Okay. If I have even powers of cosecant, right, the equivalent to the secant one, so uh, that's the equivalent to number 1 here, right? Even powers of the secant function instead 1 over secant, okay? I say the cosecant squared, I use that identity, turn everything into cotangents, then I let u equal cotangent, and the derivative of cotangent is negative cosecant squared. Again, identical to what we have uh, here. Okay, tangent and secant, instead it's cotangent, cosecant. Okay. So tangent is cotangent, negative cosecant instead of secant squared. So let's do an example. All right, so let's integrate square root of tangent times secant to the fourth. Now you might be freaking out. How am I supposed to do square root, right? I know square root is 1/2. We didn't talk anything about roots of anything. Doesn't matter. It's not odd or even, right? But my secant is, right? My secant is up here. It's even powers of secant. So this is what we'll use. I'm gonna save 1 secant, okay? The other one that's left, in my case, there's only 2. I'm gonna use the substitution, 1 plus tan squared of x. And I will let u be the tangents and plug in my derivative. Oops. So I have tan to the 1/2, right? Just to make it all into power forms to make it easier to look at for myself. I'm going to split this into 2. It said to save 1 secant squared and leave the rest, right? So in that case, there's 2 of them. I'm going to replace the secant squared with its circle identity, right? Its unit circle identity. So I have 1 plus tan squared, right? Because secant squared is this inside form. And so from here, before I multiply everything through, I could multiply through now, but let's just go ahead and say u is tangent. Derivative of u is secant squared dx, right? So the derivative, so then plugging everything in, we have u to 1/2 times 1 plus u squared, and then this is our du term. So integrating everything out, right? This goes up by 1, so 3/2. This will be, so when I multiply the 1/2 and the 2, I get 2.5, right? Or 5 over 2. So bumping that up, I get 7 over 2. Multiply the reciprocal, and this is the value that we have. Now that we have multiplied by the reciprocal, we need to go back into x. So let's go ahead and substitute back tangent for all of these u values, right? Then that is my final answer, right? So 2/3 tan to the 3/2 power of x plus 2/7 tan 7/2 power of x. All right. Hope that was helpful. I will see you guys on the next session.